If you watch the solar system from high above the North Pole of the Sun, something would strike you almost immediately. Everything is turning the same way. Every planet, every major moon, the whole system, wheeling counterclockwise in a slow, enormous rotation that has been running for 4.5 billion years. Mercury, Earth, Mars, Jupiter, Saturn, all of them spinning in the same direction they orbit, like tops that never quite fell over. The consistency of it is almost eerie. You would be looking at a pattern so clean it seems deliberate. And for the most part, scientists can explain exactly why it looks that way. Then your eye catches two planets that do not fit. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Venus rotates backward, not tilted, not wobbling, backward, the opposite direction from every other planet in the inner solar system. Uranus is something stranger still. It is tipped almost completely onto its side, rolling through its orbit at a 98-degree angle like a ball that got knocked off a shelf and never recovered. These two planets are not minor deviations. They are not rounding errors. They are profound departures from the pattern that governs everything else in the solar system, and they have kept planetary scientists arguing for decades. What makes this hard is that there is no single clean answer. Not for Venus, not for Uranus. Researchers have run simulations, built competing models, published papers pointing in opposite directions, and after all of it, the question of how these two planets ended up the way they are is still genuinely open. Some scientists think Venus was struck by a massive object early in its history, something large enough to reverse its spin entirely. Others think Venus arrived at its current state through billions of years of slow atmospheric and gravitational pressure, no collision required. For Uranus, some models point to a single enormous impact. Others suggest two. A newer theory says it might have been neither, that one of Uranus's own moons gradually dragged the planet onto its side before crashing back into it and vanishing. The scientists do not agree, and the planets are not talking. Why does this matter? Because the spin of a planet is one of the oldest facts about it. By the time a planet has existed for a few 100 million years, its rotation has largely settled. The surface evolves, the atmosphere changes, geology reshapes everything visible. But the spin rate and the spin direction mostly preserve whatever conditions the planet was born into, or whatever catastrophe hit it before the solar system quieted down. When you ask why Venus rotates backward, you are really asking about something that happened roughly 4 billion years ago, in a solar system that looked nothing like the orderly arrangement we see today. You are trying to read evidence from a crime scene where the evidence is almost entirely gone. The early solar system was not a calm place. It was full of large objects on chaotic orbits, colliding and merging and scattering each other in ways that are still being pieced together. The stable pattern we see today, everything counterclockwise, everything in roughly the same plane, is the cleaned up version. Venus and Uranus are what happens when the cleaning is incomplete. They are the loose ends. Two planets went wrong somewhere, and nobody can fully agree on why. About 4.6 billion years ago, in an unremarkable corner of the Milky Way, a cloud of cold gas and dust began to fall in on itself. This cloud was not small. It stretched across several light years, containing enough raw material to build a star and every planet around it, with plenty left over. From the outside, it would have looked like nothing at all, a dark smudge against the stars, colder than anything on Earth, barely moving. But gravity does not care how slowly something moves. It pulled the cloud inward, particle by particle, and the collapse had begun. Here is the thing about that cloud. It was not perfectly still. Nothing that large ever is. Deep inside that vast volume of gas, there were small, random swirling motions, currents drifting one way, eddies drifting another. None of them were dramatic. If you had been watching, you would have seen nothing. But when you add up all those random tiny motions across an object that size, they do not cancel out perfectly. There is always a slight leftover spin in one direction. The cloud had a net rotation. Slow, almost imperceptible, but real. That leftover spin would turn out to be the most consequential detail in the history of the solar system. As gravity pulled the cloud inward, something started happening to that slow rotation. Think about water draining from a bathtub. When water is far from the drain, it circles lazily, barely seeming to move. As it gets closer to the drain, it tightens and speeds up. By the time it reaches the center, it is spinning fast enough to see clearly. The cloud of gas behaved the same way. As it collapsed inward, pulling mass toward the center, the rotation accelerated. What had been an almost undetectable drift became a real, measurable spin. The faster it fell inward, the faster it turned. This is not a coincidence or a quirk. It is a direct consequence of a physical rule that holds everywhere in the universe, from draining bathtubs to collapsing nebulae. The rule is that the total rotational motion in a closed system cannot just vanish. If the cloud shrinks, the spin has to speed up to compensate. The details of why will come in the next section. For now, the key fact is simple. The cloud fell inward, and it spun faster the more it fell. Something else happened during the collapse. The rotation set a preferred direction. Material falling straight inward from the poles of the cloud's spin axis fell cleanly toward the center. Material coming in from the sides, near the equator, had too much sideways motion to fall straight through. It overshot. It began orbiting. Slowly, the cloud stopped being a sphere and started flattening into a disk with a dense hot center, the young sun, and a broad spinning plain of gas and dust around it. That disk is called the protoplanetary disk, and it was rotating. Everything in it was moving in the same direction, carried by the original rotation that the cloud had inherited from those tiny primordial currents, billions of kilometers across. The planets formed from that disk. Dust grains collided and stuck together. Small clumps merged into larger ones. Over millions of years, those clumps grew into rocks, then into boulders, then into bodies large enough to have their own gravity. Each one was built from material that was already moving in the same direction as the disk. Each one inherited the spin of the material it was made from. When a planet finished forming, it was rotating, and because all the material came from the same spinning disk, all the planets were rotating the same way, the same direction as the disk, the same direction as the original cloud's slow net rotation, 4.6 billion years ago. This is why the solar system looks the way it does. Mercury, Earth, Mars, Jupiter, they all spin in the same direction because they are all made of the same stuff that was moving in the same direction. It is not a coincidence, it is inheritance. The solar system is not a collection of objects that happen to agree. It is a single rotating structure whose spin has been preserved across billions of years and trillions of kilometers. The planets remember where they came from. Their rotation is a direct record of the original motion of a cold, dark cloud that most people have never thought about. The solar system was born spinning, and almost everything in it still spins the same way because of that single original rotation. The reason for all of this goes back to one of the most fundamental rules in physics, a rule so reliable that it holds from figure skaters to galaxies. It is called conservation of angular momentum. It sounds technical. The idea itself is not. Watch an ice skater spin. Arms out wide, she turns slowly. Then she pulls her arms in, close to her body, and suddenly she is spinning so fast it is almost hard to watch. She did not add any energy. She did not push off the ice again. All she did was pull her mass closer to her center, and the spin accelerated automatically. The total angular momentum of the system stayed constant. The rotation got faster because the same rotational quantity was now packed into a tighter space. This is not a trick of ice skating. It is a law. Angular momentum cannot be created from nothing, and it cannot simply vanish. It has to go somewhere. If you want to slow something down or speed it up, you need an external force acting on it. Without that force, whatever spin an object has, it keeps. The numbers change when the shape changes, but the underlying quantity is conserved. This rule holds for a spinning skater, for a collapsing star, for a cloud of gas falling inward across billions of miles. This is exactly what happened when the solar nebula collapsed. The cloud was rotating slowly, almost imperceptibly, but the rotation was there. As gravity pulled the cloud inward, the diameter shrank. The mass moved closer to the center of rotation. Exactly like the skater pulling her arms in, the spin accelerated. A slow, barely detectable drift in a cloud the size of several light years became the fast, organized rotation of a disk hundreds of millions of miles across. No new rotation was created. The original rotation was simply preserved and concentrated as the system got smaller. The planets that formed from that disk inherited the spin. Not randomly, not coincidentally. They inherited it because angular momentum had nowhere else to go. The disk was rotating in one direction, and everything that coalesced from it was rotating in that same direction. The orbital motion of the planets around the Sun, the spin of the planets on their own axes, the direction of that spin, all of it traces back to that original slow rotation of the cloud. It is the same angular momentum, carried forward across 4.6 billion years, still running. Think about what this means. When you look at a planet spinning, you are not looking at something random. You are looking at a fossil. The rotation of a planet is a physical record of the rotational state of the material it formed from. It is one of the oldest pieces of information about the solar system that we can directly measure. The Earth's spin is not an accident. It is a memory. And this is where the mystery sharpens. Because if angular momentum is conserved, and if everything formed from the same rotating disk, then everything should be spinning the same way. The default is prograde, counterclockwise when you look down from above the Sun's north pole. Every planet that formed cleanly from the disk should be spinning in that direction. Any planet spinning a different way is a planet where something interfered. Something external acted on it. Something delivered a force large enough to overcome the original rotational momentum and redirect it. Angular momentum does not reverse itself. You cannot get a prograde rotation to become retrograde without outside intervention, without a collision, without some external torque powerful enough to overcome the stored rotation of the entire object. The physics is unambiguous on this point. If Venus is spinning backward and Uranus is tilted almost completely onto its side, something had to make that happen. Something physical, something violent, or at the very least something sustained and powerful over an enormous span of time. The universe does not hand out retrograde rotations for free. Spin does not reverse itself on its own, and that is the entire problem with Venus and Uranus. Look at the solar system as a whole, and the pattern is almost impossibly clean. Every planet orbits the Sun in the same direction. Every planet, with two exceptions, also spins in that same direction. Counterclockwise, when viewed from high above the Sun's north pole. That uniformity is not a coincidence. It is the direct inheritance of a single rotating cloud of gas and dust that collapsed 4.6 billion years ago, and the planets never forgot which way that cloud was turning. Start with Mercury. It spins prograde. Slowly, one Mercurian day lasts about 59 Earth days, but in the right direction. Its axial tilt is almost nothing, less than 1 degree from perfectly vertical. It wobbles barely at all. Next is Earth, prograde, with a 23.5 degree tilt that gives us seasons, but fundamentally spinning the same way it always has. Mars is nearly identical in that respect. Its axial tilt sits at about 25 degrees, close enough to Earth's that scientists have noted the similarity for decades. And yet Mars still spins prograde, counterclockwise from above, completing one rotation every 24 hours and 37 minutes. A Martian day is so close to an Earth day that early planetary scientists found it almost suspicious. Then comes Jupiter, the largest planet in the solar system, more than twice as massive as all the other planets combined, spinning prograde at a rate that makes Earth look sluggish. Jupiter completes a full rotation in just under 10 hours. It spins so fast that it visibly bulges at the equator, flattened by its own centrifugal force. Saturn does the same. Its rotation period is about 10.5 hours, also prograde, also fast enough to flatten the poles and widen the middle. You can see the bulge in photographs. Even Neptune, at the outermost edge of the solar system, spins prograde. Its rotation period is roughly 16 hours. Its axial tilt is 28 degrees, a bit more than Earth's, but still fundamentally pointing upright, still counterclockwise from above. What makes this striking is not just that most planets are prograde, it is how prograde they are. The axial tilts vary. Earth at 23.5 degrees, Saturn at 26.7, Mars at 25, Neptune at 28. But in every case, the planet is recognizably upright. The spin axis points more or less perpendicular to the orbital plane. The tilts are enough to produce seasons, enough to shift climate patterns dramatically, but not enough to scramble the basic geometry. You can still tell which way is up. You can still trace the original rotation of the solar nebula in every one of them. This consistency is itself a piece of evidence. When you see the same pattern repeated across 8 planets spread over billions of kilometers, you are not looking at a series of independent events. You are looking at a common origin. The shared prograde rotation is a fossil of the same angular momentum that was baked into the system from the beginning. Each planet conserved that spin as it formed. The physics did not forget. Even the planets scientists once thought were exceptions turned out to be less exceptional than believed. Neptune's tilt of 28 degrees seemed unusual at one point. It is not. It fits within the normal range without trouble. These are not anomalies. These are variations on a theme, and the theme is clear. Then there is Venus, and there is Uranus. Both are planets in the same solar system, formed from the same disk, governed by the same physics. And both look, in terms of rotation, nothing like the others. Not slightly off, not tilted a few extra degrees past the comfortable range. Completely, structurally different in ways that demand a separate explanation. The contrast between the orderly lineup of Mercury, Earth, Mars, Jupiter, Saturn, and Neptune, and the behavior of those two is not subtle. It is the kind of contrast that stops you and makes you ask what could possibly have happened. And then there are the two that look like they were placed there by a different universe entirely. Venus and Uranus are the two planets that refuse to follow the rules, but they refuse in very different ways. Every other planet in the solar system inherited the same basic spin from the same rotating cloud of gas and dust and stayed that way. These two did not. What makes them interesting is not just that they are wrong. It is how specifically, how dramatically, how completely wrong they are. And the fact that they are wrong in entirely different directions suggests that whatever happened to one of them probably had nothing to do with what happened to the other. Start with Venus. From above the solar system's north pole, Venus orbits the Sun counterclockwise, exactly like every other planet. But if you watched it spin on its own axis, it turns the other way, clockwise, backward. This is what astronomers call retrograde rotation, and Venus is the clearest example of it in the solar system. The Sun rises in the west on Venus. It sets in the east. Every instinct built into any creature that ever evolved on Earth would read that sky wrong. And the spin is not just backward, it is extraordinarily slow. One full rotation takes 243 Earth days. That number is hard to feel until you stack it against something familiar. A year on Venus, one complete trip around the Sun, takes only 225 Earth days. The planet rotates more slowly than it orbits. A Venusian day is longer than a Venusian year. That single fact sits at the edge of what seems geometrically possible, and Venus is doing it without any drama, just turning backward, slowly, in the dark. Then there is Uranus, which is a completely different kind of wrong. Uranus is not spinning backward, it is spinning sideways. Its axial tilt is 97.8 degrees. For comparison, Earth is tilted at 23.5 degrees, which gives us our 4 seasons. Mars is tilted at about 25 degrees. Saturn, which looks dramatically tilted in telescope images, sits at 26.7 degrees. These planets are all recognizably upright. Uranus is not upright. It is lying almost flat on its side relative to its orbital path, its poles pointing roughly toward and away from the Sun instead of up and down. If you watched it from above, it would look less like a spinning top and more like a ball rolling along a track. Every other planet in the solar system rotates the way a top does. Uranus rolls. This is where the two planets diverge sharply as a puzzle. Venus has almost no axial tilt at all, only about 3 degrees. Its poles point in roughly the right direction. Its problem is purely directional. It is spinning the correct way geometrically, just in the opposite rotational sense. Uranus, on the other hand, has the direction almost right by one convention, but the geometry completely obliterated. Its poles are where its equator should be, These are not the same malfunction. They do not suggest the same history. A single explanation that accounts for both of them would be suspicious, because the two anomalies look like they came from completely separate events billions of years ago, events that left very different fingerprints. This is part of why planetary scientists find them so useful to think about together. They are a natural pair of case studies, two data points in a question about how often the early solar system was violent enough to permanently rewrite a planet's spin. Studying one without the other misses something, and studying them together makes it clearer that the solar system's orderly appearance today is a cleaned-up version of something that was, for a long time, much more chaotic than anything we can directly observe now. Two planets, two separate mysteries, and the explanations that scientists have assembled for each one are stranger than you might expect. Venus and Earth are almost the same size. The difference in their diameters is less than 650 kilometers. Their densities are nearly identical. Their bulk compositions are similar enough that for a long time, planetary scientists assumed the two worlds had formed under roughly the same conditions and evolved along roughly the same path. Venus was Earth's twin, just a little closer to the Sun. That picture turned out to be wrong in almost every way that matters. The most immediate problem is the spin. Earth rotates from west to east. Stand anywhere on the surface and watch the sky long enough. The sun rises in the east and sets in the west. That direction of rotation, counterclockwise when viewed from above Earth's north pole, is the standard. It is the direction inherited from the original solar nebula, the direction that almost every other body in the solar system shares. Venus rotates the other way, east to west. The Sun, from Venus's surface, would crawl up over the western horizon and sink toward the east. That single fact puts Venus in a category almost entirely by itself. And the rotation is not just backward, it is extraordinarily slow. One full rotation of Venus takes 243 Earth days. To feel how long that is, consider that a human pregnancy runs about 280 days. The time it takes Venus to spin once on its axis is close to the time it takes to carry a child from conception to birth. Most people spend 243 days passing through roughly 8 months of their life, the end of 1 year, through winter, into spring. Venus uses all of that time just to turn around once. For comparison, Earth completes a full rotation in 24 hours. Mars takes just over 24.5 hours. Jupiter, despite being enormously larger, spins once every 10 hours. Venus sits at the extreme slow end of the solar system. Nothing else among the major planets comes close to this pace. The number is not just unusual, it is genuinely hard to account for within standard models of planetary formation, and the slowness and the backwardness together make Venus an object that demands an explanation. There is another important difference between Venus and Uranus, the other planet with a serious spin problem. Uranus is tilted nearly 98 degrees, essentially knocked sideways so that its poles point more or less at the Sun. Venus is not tilted like that. Its axial tilt is just 3 degrees, almost perfectly upright relative to its orbital plane. The wrongness in Venus's spin is not about angle. The planet is not leaning dramatically one way or another. It is simply turning in the wrong direction, cleanly, with almost no wobble. Backward, but upright. That distinction matters because it means Venus and Uranus almost certainly arrived at their unusual states through different histories. For a long time, nobody actually knew Venus was rotating backward. The problem is that Venus is completely hidden beneath a permanent, impenetrable layer of cloud. Thick sulfuric acid clouds cover the entire planet at all times. No optical telescope, no matter how powerful, has ever seen the surface of Venus from Earth. Early astronomers could track Venus's position in the sky and observe the planet's phases like a tiny gibbous moon, but the surface itself was invisible. Estimates of Venus's rotation period from visual observation were wildly wrong for decades. Some astronomers guessed it might rotate in about the same time as Earth. The truth came from radar. In the early 1960s, radio telescopes on Earth began bouncing radar signals off Venus's surface and measuring the returning signals. Radar penetrates cloud cover easily, and by analyzing how the returning pulses were shifted by the planet's rotation, the same Doppler principle used in weather radar, scientists could measure the spin directly. What they found was startling. The rotation was slow, far slower than anyone expected, and it was retrograde. The confirmation came from several independent radar studies across multiple facilities, and by the mid-1960s, the result was established. Venus turns the wrong way. So the picture of Venus is this: a planet nearly identical to Earth in size and density, sitting close enough that on a clear night, it is the brightest object in the sky after the sun and moon, yet spinning silently backward at a pace so slow it borders on geological. Its surface hidden. Its behavior unlike anything predicted. On the inside, it looks like a twin, and on the outside, it behaves like a stranger. One of the strangest consequences of Venus's rotation is that its day is longer than its year. That sentence sounds like it should be wrong. It feels like the kind of thing you misread, but the numbers are real, and they hold up under examination. Venus takes 243 Earth days to complete a single rotation on its axis. It takes only 225 Earth days to complete one full orbit around the Sun, which means Venus travels all the way around the Sun, returning to the same point in space before it has finished spinning once. The planet laps itself. Its year ends before its day does. To understand why this gets even stranger, you have to separate two different kinds of days. There is the sidereal day, which is how long a planet takes to rotate once relative to the distant stars. And there is the solar day, which is the time between one sunrise and the next, the length of a day as you would actually experience it standing on the surface. On Earth, these two numbers are close, but not identical. Our sidereal day is 23 hours and 56 minutes. Our solar day is 24 hours. The gap exists because while Earth is rotating, it is also moving along its orbit, so the Sun appears to shift slightly against the stars each day, and Earth needs about 4 extra minutes of rotation to bring it back into position. The difference is small. Most people never think about it. On Venus, the difference is not small. Venus's sidereal day is 243 Earth days, but Venus is also rotating backward relative to its orbit. It moves around the Sun in the standard prograde direction while spinning in the opposite direction. Those two motions are working against each other, and the result compresses the solar day dramatically. A sunrise on Venus occurs not every 243 days, but roughly every 117 Earth days. The sidereal day and the solar day on Venus are nearly cut in half by the geometry of a planet moving forward in its orbit while spinning in reverse. If you stood on the surface and watched the sky, the sun would crawl from one horizon to the other across a span of roughly 117 Earth days. That is the length of a Venusian day, as felt by anyone on the ground. 4 months per day. Put that number next to something familiar. A human pregnancy lasts around 280 days. A single Venusian day is nearly half of that. The entire summer in the Northern Hemisphere runs about 93 days. One Venusian day is longer. The Voyager 1 spacecraft, launched from Earth, took about 64 days to reach Jupiter. On Venus, the sun would not yet have set, and within that 117-day cycle, morning alone accounts for roughly 58 days. The sun rises, infinitely slowly, dragging itself across the sky over the course of weeks. The angle of light changes in ways too gradual for a human observer to register in real time. There is no golden hour on Venus. There is a golden month. The light that falls across the surface during what we would call morning falls for nearly 2 Earth months before the sun reaches anything close to noon. Then it takes another 2 months to drift toward the horizon on the other side and disappear. There is another layer of strangeness sitting inside this. During those 117 Earth days of a solar day, the planet has almost completed its year. One full orbit around the sun takes 225 Earth days. A single day, sunrise to sunrise, is 117 of those. So you get about 2 sunrises per Venusian year, 2 mornings, 2 afternoons, 2 sunsets. That is the annual rhythm of Venus. On Earth, a year contains 365 days. On Venus, a year contains barely more than 2. This is not a quirk of how you choose to measure time. It is a physical consequence of Venus spinning as slowly as it does, in the direction that it does, relative to the path it follows around the sun. The geometry produces it. The numbers cannot be arranged any other way, and the consequence plays out in full every year on Venus, silently, with no one watching. The sun rises over Venus roughly twice per Venusian year, and when it does, it rises in the west. Each sunrise begins a morning nearly 2 months long. A single morning on Venus lasts longer than most of the pregnancies of most animals on Earth. If you could stand on the surface of Venus, which you could not survive for more than a few minutes, the first thing you might notice about the sky would be wrong. Not the heat, though the heat would kill you. Not the pressure, though 90 atmospheres would crush you like the bottom of an ocean. The first wrong thing would be simpler and stranger than either of those. The sun would be rising in the west. Every instinct a human has about morning is built on one assumption. East is where the light comes from. Every culture on Earth has organized time, navigation, and language around that single fact. Temples face east. Explorers used it as a fixed direction. The word Orient comes from the Latin for east, the direction you face to find your bearings. On Venus, none of that works. The sun climbs out of the western horizon and tracks slowly, almost imperceptibly slowly, toward the east. If you watched it for an hour, you might not be certain it had moved at all. The rotation is so sluggish that the sun covers less than a single degree of sky per Earth day. What the sun looks like from below Venus's clouds is its own separate strangeness. You would not see a sharp disk. There are no clear skies on Venus. The atmosphere is a permanent, planet-wide overcast of thick sulfuric acid clouds layered roughly 50 kilometers above the surface. The light that reaches the ground has been scattered, filtered, and dimmed until it arrives as a diffuse orange-yellow glow from no particular direction. Shadows on Venus would be soft, nearly invisible. There is no moment of sunrise the way we know it, no crisp line of light breaking the horizon. The sky simply brightens, slowly, over the course of what would be many Earth days, from one shade of orange murk to a slightly lighter shade of orange murk. The temperature at the surface is around 465 degrees Celsius. That is hot enough to melt lead. It is hotter than the surface of Mercury, despite Mercury being far closer to the Sun, because Venus's thick atmosphere traps heat with an efficiency that nothing else in the solar system matches. The atmospheric pressure is 90 times what you experience standing at sea level on Earth. Standing on Venus would feel something like being submerged 900 meters underwater, except the water is carbon dioxide and it will also cook you. And through all of that, the sun is still rising in the west. That detail does not get easier to absorb. Venus is roughly the same size as Earth, made of roughly similar rock, sitting at a not impossible distance from the sun. It is the planet that looks most like a twin on paper. Then you look at the sky and everything falls apart. The direction of morning is reversed. The star at the center of the solar system rises from the wrong horizon, moves too slowly to track, and glows through clouds that would dissolve your eyes before you had time to look up. A human standing there, if survival were somehow possible, would have no reliable instincts to fall back on. Everything learned from living on this planet would give the wrong answer. The nearest planet to Earth has a sky that no human instinct is built to read. The most straightforward explanation for Venus's backward spin is also the most violent one. Early in the solar system's history, the planets were not the only large objects orbiting the Sun. The space between them was crowded. Protoplanets, rocky bodies that had grown to sizes somewhere between a small moon and a full planet, were moving on crossing orbits, colliding, merging, breaking apart, and occasionally hitting something large enough to change everything. The final stages of planet formation were not a quiet process of gradual accumulation. They were a demolition derby running at planetary scale, and Venus almost certainly did not survive it untouched. The leading hypothesis is simple in its outline. At some point in Venus's early history, a body large enough to matter, probably somewhere in the range of Mars-sized or bigger, struck Venus directly. The impact carried enough angular momentum to overwhelm whatever spin Venus had inherited from the solar nebula and replace it with something new. The math works. An object of sufficient mass, hitting at the right angle with enough velocity, can do exactly that. It can take a planet spinning one way and leave it spinning the other way, or leave it barely spinning at all, or both. Venus today does both. It rotates backward and it rotates extraordinarily slowly, and a single large collision can explain both facts at once. The parallel to Earth's own history is hard to ignore. Earth also experienced a giant impact. Roughly 4.5 billion years ago, in the same chaotic period when Venus would have been vulnerable, the early Earth was struck by a protoplanet called Theia, estimated at roughly the size of Mars. The collision was oblique, a glancing blow rather than a direct hit. It threw an enormous quantity of material into orbit around Earth, and that material eventually coalesced into the Moon. The Moon is essentially the frozen debris field of one of the most catastrophic events in Earth's history. It has been orbiting ever since as a permanent record of what happened. Venus has no moon. That absence is significant. Simulations of giant impacts on Venus show something interesting. When researchers model collisions that reproduce Venus's current rotation rate and direction, the debris patterns that result are unlike the ones that produced Earth's moon. In the Earth-Moon scenario, the impact left behind a substantial ring of material outside Earth's synchronous orbit, and that material had enough time and space to accrete into a single large moon. In Venus scenarios that match the observed rotation, the debris tends to behave differently. The material falls back. It reaccretes onto Venus itself rather than forming a stable ring in orbit. The simulations suggest that the kind of impact that could have reversed Venus's spin is also precisely the kind of impact that would not leave a moon behind. The planet collects the wreckage. Nothing persists in orbit long enough to build anything. This is not a coincidence the researchers are ignoring. It is one of the strongest pieces of supporting evidence the giant impact hypothesis has. Venus lacks a moon, and the model predicts it should lack a moon. That alignment between prediction and observation matters. The range of impact scenarios that work is actually surprisingly wide. Researchers have run models with head-on collisions and with oblique, hit-and-run impacts. They have tested impacts on a non-rotating Venus and on a Venus already spinning prograde at various speeds. Across a broad range of impactor sizes and approach angles, a significant fraction of scenarios produce a final rotation consistent with what Venus shows today. The hypothesis does not depend on one very specific set of conditions. It is robust across the parameter space. That breadth makes it harder to dismiss. What the simulations cannot tell us is exactly which version of the impact actually happened. A head-on strike by a large body on a slow Venus looks different from an oblique hit-and-run by a faster, smaller one. Both can get you to the same place. The final rotation of Venus does not uniquely identify the impactor. The forensic evidence points to the crime, but not to a single weapon. What it does tell us is that the early solar system was dangerous in a way that is difficult to fully absorb. The objects wandering those orbits 4.5 billion years ago were not small. Theia was large enough to help create the moon. Whatever hit Venus, if anything did, was in the same category. These were not collisions between rocks. They were collisions between worlds. The energy released in an impact of this scale is enough to melt the surface of a planet, reset its geology, and permanently alter the direction of its spin. Both Venus and Earth carry the marks of this era. Earth's mark orbits overhead every night. Venus's mark is the direction it turns, slow and backward, every 243 days. Earth got a moon from its giant impact, and Venus got a backwards rotation, and both outcomes were probably written in the same chaotic ledger of early solar system collisions. Some researchers have a completely different answer for Venus, one that requires no catastrophic collision at all, no incoming object, no ancient scar buried beneath the clouds. In this model, Venus arrived at its current backward spin the same way water carves a canyon, slowly, continuously, through forces that never stop pressing. The violence is not missing from the story. It just operates at a timescale that is almost impossible to hold in your mind. The first force is gravity. Venus orbits the Sun at an average distance of about 108 million kilometers, roughly 70% of Earth's distance. That closeness matters enormously. Gravity weakens with distance, and because Venus sits so much nearer to the Sun than Earth does, the Sun's gravitational pull on Venus is significantly stronger. That pull does not act evenly on the whole planet. The side of Venus facing the Sun gets pulled a little harder than the far side. This difference creates a stretching effect, a tidal force, and that force generates a torque on the planet's rotation. The same mechanism that controls Earth's tides in the ocean is working on Venus itself, tugging at the body of the planet, trying to slow its spin. Given enough time, this kind of tidal braking tends to push a planet towards synchronous rotation, where one face permanently looks at the Sun and the rotation period exactly matches the orbital period. The Moon is already there. It keeps one face locked toward Earth because Earth's tidal forces have been working on it for billions of years. The Sun has been doing something similar to Venus, just not quite finishing the job. But gravitational tides alone cannot account for Venus's backward spin. Tidal locking would produce a slow prograde rotation, not a retrograde one. Something else has to push in the opposite direction. That something is the atmosphere. Venus has one of the most extreme atmospheres in the solar system. The surface pressure is about 92 times what you would experience on Earth. The atmosphere is mostly carbon dioxide, and it is dense enough that it behaves almost like a slow ocean. When the Sun heats the day side of Venus, this massive atmospheric blanket warms and expands. When the sunlit side of the atmosphere heats up and the night side stays cooler, the atmosphere develops its own large-scale pressure variations, a wave of slightly higher and lower pressure that rotates with the position of the Sun. This is called a thermal atmospheric tide. The thermal tide creates a torque on the planet, and the direction of that torque is retrograde. The atmosphere, heated by the Sun on one side, pushes back against the planet's rotation in the opposite direction from the gravitational tide. So you have two competing forces: gravitational tides trying to slow Venus and lock it into prograde synchronous rotation, atmospheric tides pushing it toward retrograde. The question is, which one wins? And the answer appears to be that neither one completely dominates. They reach a balance, and the place where they balance turns out to be close to where Venus sits right now, rotating backward very slowly, with a period of 243 Earth days. This is not a coincidence that researchers found by accident. When scientists built mathematical models of both torques and ran them forward billions of years, starting with a hypothetical early Venus spinning prograde at a reasonable rate, they found that the rotation naturally evolves toward equilibrium states. The equations allow for several possible stable endpoints, and one of them closely matches what we actually observe. Venus's current rotation may not be random or the residue of a catastrophic hit. It may be the natural destination of a planet caught between two persistent forces, like a pendulum finding its resting angle. What makes this theory particularly striking is what it does not require. There is no need to invoke a massive impactor arriving at just the right angle with just the right mass. There is no collision to explain, no surviving evidence to search for. The entire explanation runs on physics that is already operating in the solar system right now, at a timescale that simply exceeds human intuition. 1 billion years is long enough for a very gentle torque to move a planet a very long way. Were there problems with this model? Some. Early versions struggle to account for exactly how Venus's initial prograde spin would have been brought all the way through zero and into retrograde territory, rather than just break to a halt. Later and more detailed models, incorporating a thicker early atmosphere and better estimates of Venus's interior structure, showed that the transition is plausible, though still not perfectly constrained. The numbers are sensitive to assumptions about Venus's interior, and Venus's interior is poorly understood. But the core picture holds up. A young Venus spinning prograde, gradually slowed by solar tides, simultaneously pushed retrograde by its own dense atmosphere, eventually settling into the slow backward roll we measure today. In this picture, Venus was not struck backward. It was slowly nudged there by physics operating without any violence at all, over billions of years, one tiny push at a time. The stranger part of the Venus story is not just that it rotates backward, but that it rotates backward at almost exactly the rate that the physics predicts it should. That is not a small detail. When researchers ran the equations describing how gravitational tides and atmospheric tides compete against each other on Venus, they did not get a single answer. They got four distinct rotational states where the competing forces balance out and the spin stabilizes. 4 equilibrium points, like valleys in a landscape where a rolling ball will eventually come to rest. 2 of them are prograde, 2 of them are retrograde. And Venus sits almost exactly on top of one of the retrograde options, at 243 days per rotation, matching the theoretical prediction with a precision that stopped researchers cold when they first worked it out. To understand why this matters, you have to think about what an equilibrium actually means in this context. On Venus, gravitational tides from the Sun are constantly pulling on the planet's solid body, trying to slow its spin down and eventually lock it face forward toward the Sun, the way the Moon is locked toward Earth. That force points in one direction. But Venus also has an atmosphere 90 times denser than Earth's. That atmosphere heats up on the day side and cools down on the night side. Pressure differences that drive a slow atmospheric rotation. Those thermally driven atmospheric tides push the spin in a retrograde direction. The 2 forces are pulling against each other constantly, and where they reach a standoff, the rotation stabilizes. The math shows those standoffs occur at 4 specific rotation rates. The 2 prograde equilibria would place Venus spinning in the same direction as its orbit, one faster and one slower. The 2 retrograde equilibria place Venus spinning backward. The slower of those 2 retrograde options lands almost exactly at 243 Earth days. That is where Venus is right now. The match between prediction and observation is close enough that many researchers consider it the strongest evidence that tidal and atmospheric forces, not a catastrophic ancient collision, are the primary drivers of how Venus ended up spinning the way it does. What this framework also opens up is a picture of Venus's history as something more than a fixed fact. If there are 4 possible stable states, Venus could have occupied different ones at different times. Early in the solar system's history, when Venus had just formed and inherited a prograde spin from the original rotating disk, it would have been nowhere near any of these equilibrium points. Over millions of years, the competing torques would have slowly pushed and pulled that rotation rate, nudging it toward the nearest equilibrium. Whether it settled into a prograde state first and later transitioned to a retrograde one, or moved more directly toward its current configuration, depends on conditions in the early Venusian atmosphere that scientists do not yet have clean measurements for. The atmosphere is the critical variable. The strength of the atmospheric tide depends on how dense Venus's atmosphere was billions of years ago, and how strongly it responded to solar heating. A thinner early atmosphere would have produced weaker atmospheric tides. That might have allowed gravitational tides to dominate and pull Venus toward a prograde lock instead. If Venus's atmosphere thickened over time through volcanic outgassing, the balance of forces would have shifted, potentially pushing the rotation through one equilibrium and toward another. In this reading, Venus did not simply arrive at 243 days and stop. It may have passed through other stable states on the way there, held for a while, then been nudged forward again as conditions changed. This picture makes Venus's rotation feel almost like a negotiation, not a single violent event, not a random outcome, but the result of two physical forces working against each other across geological time until the planet found a configuration both forces could live with. The 243-day number is not arbitrary. It is the answer the physics keeps arriving at when you put a planet of Venus's mass and atmospheric density at Venus's distance from the Sun and let the equations run. That precision is either an extraordinary coincidence or the clearest sign we have that Venus's current rotation is not an accident, but a destination. After decades of study, the honest answer about Venus is that the case is not closed. Two competing explanations exist. Both are mathematically consistent with what we observe. Both have supporters at major research institutions. And after all the telescope time and simulation runs and published papers, scientists still cannot say definitively which one is right. That is not a failure of science. It is an honest description of where the problem actually stands. The giant impact hypothesis says something enormous struck Venus early in the solar system's history and either reversed its spin outright or hit it hard enough to set it rotating so slowly that tidal forces finish the job. The atmospheric and tidal evolution hypothesis says no catastrophic collision was necessary at all, that Venus arrived at its current rotation gradually, pushed there by the competing torques of solar gravity and its own thick atmosphere over billions of years. Both models produce a slowly rotating retrograde Venus. Both are consistent with the 243-day rotation period. The observations do not cleanly discriminate between them. Part of why this is so hard to resolve comes down to Venus's surface. The planet resurfaces itself constantly through volcanic activity. Lava flows cover old terrain. Impact craters get buried. The geological record that might tell us something about Venus's early history is largely erased, written over by hundreds of millions of years of ongoing volcanic resurfacing. Earth at least has ancient rocks. Venus has almost none. Its surface looks geologically young, even though the planet itself is 4.5 billion years old. Whatever happened in Venus's first billion years is essentially gone. The interior is another problem. To properly calculate the atmospheric tidal torque, you need to know how Venus's interior responds to tidal forcing. That depends on the viscosity and structure of the mantle. Right now, those numbers are poorly constrained. We have never sent a lander that survived long enough to do serious seismic work on Venus. The surface pressure is 90 times that of Earth, and the temperature sits around 465 degrees Celsius. Every lander the Soviets dropped there in the 1970s and 1980s died within about 2 hours. Without better interior data, the tidal models carry significant uncertainty, and that uncertainty is wide enough for both hypotheses to fit inside it. The atmospheric measurements have their own gaps. The thick cloud layers that blanket Venus make direct observation of the surface impossible in visible light. Radar has given us topographic maps, but the atmospheric dynamics at depth are not fully characterized. The thermally driven atmospheric tides that sit at the heart of the gradual evolution model need to be measured more precisely before anyone can say with confidence how strong they are and whether they are strong enough to do what the model requires. Here is the other complication. These two hypotheses are not necessarily in competition. A giant impact and gradual tidal evolution are not mutually exclusive. A large collision could have struck Venus early and left it rotating slowly in a prograde direction, or slightly retrograde, and then atmospheric tidal forces spent the next several billion years pushing it further into the configuration we see today. The impact sets the initial conditions. The tidal forces do the slow fine-tuning. In this combined picture, both camps are partially right, and the real question becomes not which one happened, but how much each one contributed. That question is genuinely difficult to answer with the data currently available. Future missions to Venus, including several in planning and development, may change this. Better atmospheric measurements, more detailed gravity data, and eventually seismic readings from a lander that can survive the surface environment long enough to be useful would all help constrain the models. But for now, Venus sits in a strange position in the literature. A planet studied intensely for decades, with two solid explanations that both fit and no clean way to choose between them. The rotation of Venus is real, measurable, and deeply strange. Why it is that way remains genuinely open. And then there is the other planet, the one where the wrongness is not backward but sideways, and the scale of it is in some ways even harder to explain. Uranus has the most dramatic rotational problem in the solar system. Venus rotates backward. That is strange. But Uranus has done something that makes Venus look almost reasonable by comparison. Uranus is lying on its side, not tilted a little, not leaning at an unusual angle. Lying on its side, with its poles pointed almost directly toward and away from the Sun, rolling through its orbit like a ball across a floor, rather than spinning upright like a top. To feel how strange that is, you need a reference point. Earth has an axial tilt of 23.5 degrees. That tilt is why seasons exist. As Earth travels around the Sun, different hemispheres lean toward it and away from it, receiving more or less direct sunlight across the year. Mars is tilted 25.19 degrees, almost identical to Earth. Saturn is tilted 26.73 degrees. These numbers cluster together. None of them are extreme. They represent a planet that is mostly upright, spinning with its axis pointed roughly perpendicular to its orbital plane, with a modest lean built in, a top with a slight wobble. That is the normal picture. Now consider Uranus. Its axial tilt is 97.8 degrees. That number does not just sit outside the normal cluster, it is in a completely different category. A tilt of 90 degrees would mean the planet's axis is perfectly horizontal, lying flat in the orbital plane. Uranus exceeds that by nearly 8 degrees, which means Uranus is not just lying on its side. It is tilted slightly past sideways. Its poles dip below and above the orbital plane, and as the planet moves around the Sun, one pole sweeps toward the Sun, and then the other does, in a cycle stretching across decades. Picture the solar system from above. Most planets are spinning like tops, each one upright, rotating counterclockwise when viewed from above the north pole of the Sun. Then there is Uranus, rolling along its orbital path like a barrel, its rotational axis nearly parallel to the plane of the solar system instead of perpendicular to it. It does not spin in the same sense that the other planets spin. It tumbles. The visual is almost physically unsettling once you hold it in your mind. This geometry creates a technical classification problem. When astronomers define the north pole of a planet, they have a choice. One convention uses the right-hand rule, a standard physics definition tied to the direction of rotation. Under that rule, Uranus's north pole points in a direction that makes its rotation retrograde. In other words, it spins in the opposite direction from its orbit. This technically places Uranus in the same backward spin category as Venus, though the geometry that produced this result is entirely different. Venus is upright and spinning the wrong way. Uranus is sideways and tumbling through space in a way that the North Pole convention cannot cleanly capture without qualifying everything. The numbers help anchor this. If Uranus had Earth's 23.5-degree tilt, its poles would swing no more than 23.5 degrees toward or away from the Sun over the course of a year. At 97.8 degrees, the poles swing all the way past perpendicular and point nearly straight at the Sun for portions of the planet's 84-year orbit around it. That is not a seasonal variation. That is a fundamental reorientation of the entire planet relative to its star. What caused this? Nobody knows for certain. The leading ideas involve giant collisions, migrating moons, or some combination of catastrophic events early in the solar system's history. Those explanations are coming, but the geometry itself is the first thing to take seriously, because it is easy to read 97.8 degrees and not fully register what it means. It means a planet where the concept of a North Pole and a South Pole almost loses its intuitive meaning. It means seasons that last not months, but decades. It means a planet that the solar system's standard rules apply to only awkwardly, with footnotes and exceptions and asterisks attached to nearly every description. There is nothing in the solar system that looks like Uranus when it comes to rotation. Not even Venus, which rotates slowly backward in a way that is at least geometrically familiar, produces this sensation of a planet fundamentally misaligned with everything around it. It does not spin wrong so much as it fell over and stayed there, rolling through space at an angle that nothing else in the solar system comes close to matching. The consequences of Uranus's tilt are hard to picture until you work through them slowly. Start with the basic geometry. Uranus orbits the Sun once every 84 Earth years. Its axis is tilted nearly 98 degrees from vertical. That means its poles don't point up and down the way Earth's do. They point sideways, roughly toward and away from the Sun. As Uranus crawls through its long orbit, one pole faces the Sun almost directly for about 42 years. The other pole sits in complete darkness for the same stretch. Then the planet rolls far enough around its orbit that the situation reverses. The dark pole swings into the light. The lit pole slides into shadow. And that cycle, pole to pole, takes the full 84 years to complete. Stand at the north pole of Uranus during its summer solstice, and the Sun sits near the zenith. It doesn't rise. It doesn't set. It just hangs there, day after day, year after year, for decades. There is no night. There is no rotation of light across a sky the way you'd expect on any normal planet. The Sun traces a slow, shallow spiral as Uranus rotates beneath it, but it never dips below the horizon. The same face of the planet just keeps absorbing light for 42 straight years. Then the orbit shifts. The Sun drops toward the horizon, finally crossing it. And what follows is 42 years of darkness, uninterrupted, absolute. No sunrise is coming soon. The next one is 4 decades away. At the South Pole, the same story runs in reverse. While the North bakes in decades of sunlight, the South sits in a polar night so long it stretches across most of a human lifetime. Children born into that darkness on a hypothetical Uranian surface would grow old before the Sun appeared. The concept of a day or a night in any ordinary sense becomes almost meaningless. Time at the poles of Uranus is measured not in hours, but in generations. Move away from the poles toward the equator, and the picture changes. During Uranus's solstice, an observer standing on the equator would watch the Sun skim low along the horizon, never rising high into the sky, spending most of the rotation period either set or barely visible. The equatorial regions receive less energy during solstice than almost any other latitude on the planet, which is the opposite of how it works on Earth, where the equator is the warmest zone year-round. On Uranus, during solstice, the poles are the places soaking up the most sunlight. The equator is essentially a cold, dim band. The seasons on Uranus around its equinoxes are the closest the planet gets to anything resembling normal. Twice per 84-year orbit, as Uranus passes through the equinox points, its equator faces roughly toward the Sun. During those transitions, the Sun rises and sets in something like a recognizable rhythm. Days and nights alternate. The sunlit hemisphere shifts from one side to the other. For a window of time around the equinox, conditions at the equator approach what you might call standard planetary behavior. But that window is narrow in the context of an 84-year orbit. Within a few years, the tilt carries the pole back into direct sunlight, and the long extremes resume. Voyager 2 flew past Uranus in 1986, arriving during the planet's southern summer solstice. The South Pole was aimed almost directly at the Sun. The spacecraft was essentially looking down at the sunlit pole as it approached, and what it found was a surprisingly featureless, blue-green disk. Scientists expected dramatic atmospheric activity from the uneven heating. What they saw instead was almost placid. The atmosphere was not responding the way models predicted. Part of what made this puzzling is how sluggishly Uranus's atmosphere transfers heat. Despite one pole absorbing light continuously for decades, the temperatures at the two poles are not as different as you might expect. The planet's atmosphere spreads energy around slowly, and the result is a world whose extremes of illumination don't translate neatly into extremes of temperature. The geometry is violent. The response is almost eerily calm. Uranus takes about 84 years to go once around the Sun, which means humans living through a full Uranian year would need to reach the age of 84 to witness every seasonal phase. Most people alive on Earth today were not yet born the last time Uranus was in the same part of its orbit it occupies right now. The 2007 equinox was the most recent moment when both hemispheres received roughly equal sunlight. Since then, the northern pole has been tipping progressively into sunlight. The northern summer solstice won't arrive until around 2030. At that point, the North Pole will be aimed almost directly at the Sun, and the South Pole will be beginning its 4-decade night. And none of this is new. This same cycle has been running since Uranus settled into its tilted orientation billions of years ago, long before the Earth had cooled, long before any ocean existed on any world. It is the most alien seasonal pattern in the solar system, and it has been playing out for billions of years before any eye existed to observe it. The most widely cited explanation for Uranus's tilt is also the simplest. Something enormous hit it. Early in the solar system's history, roughly 3 to 4 billion years ago, the outer solar system was crowded with large rocky and icy bodies still moving on unstable orbits. Planet formation was not finished. Protoplanets the size of Earth or larger were still crossing each other's paths. Collisions at that scale were not unusual events. They were, in a real sense, how the solar system was finishing itself off. Each giant impact either building something bigger or permanently altering whatever it struck. The leading theory says Uranus drew the unlucky collision. Something massive hit it at an angle sharp enough to tip the planet almost completely onto its side, and the tilt has been locked in ever since. What makes this explanation compelling is that it does not require any exotic physics. Angular momentum can be transferred through a collision. If the impactor is large enough and hits at the right angle, the resulting change in spin axis can be dramatic and permanent. Researchers have run the numbers. Jacob Kegereis at Durham University led a detailed simulation effort that tested dozens of impact scenarios against what we observe today. His team found that an impactor somewhere between 1 and 3 Earth masses, striking Uranus at a steep enough angle, could account for the current 97.8-degree tilt. The models did not require a perfectly aimed shot. A fairly wide range of impact geometries produced outcomes close enough to Uranus's actual orientation. That flexibility is part of what makes the collision hypothesis durable. It does not depend on one exact configuration having occurred. The broader context also supports it. Scientists who study planetary formation have come to understand that the final stage of building planets is dominated by exactly this kind of violence. The technical term is the giant impact stage. Once most of the mass in a region of the solar system has gathered into a handful of large bodies, those bodies inevitably collide. They cannot all stay on stable orbits indefinitely. The math does not allow it, so they find each other. Earth's moon almost certainly formed from one of these collisions. Mars's moons are probably captured debris from another era of this same process. Venus's backward spin, as discussed earlier, may come from its own giant impact. Uranus being struck hard enough to rotate at 98 degrees is consistent with everything we know about how the outer solar system cleared itself out. The timing matters too. Simulations of the early solar system suggest that the outer planets were not always in their current positions. Jupiter and Saturn's gravity reshuffled a great deal of material, sending large bodies inward and outward, crossing orbits that had previously been stable. This migration is thought to have sent a wave of debris through the solar system during what some researchers call the Late Heavy Bombardment, a period of intense collisions roughly 4 billion years ago. Uranus was sitting in the middle of all that. An encounter with a large stray protoplanet during this period is not a stretch. It is close to what the models predict should have happened to at least some of the outer planets. There is also something specific about how hard Uranus was hit that the simulations have tried to pin down. A glancing blow would tilt the planet, but might not completely restructure its outer layers. A more direct impact would dump enormous heat into the planet's interior. Some researchers have pointed out that Uranus is surprisingly cold compared to Neptune. It radiates almost no internal heat, while Neptune radiates significantly more than it receives from the Sun. One possible explanation is that the impact that tipped Uranus also created a layer in its interior that traps heat, preventing it from escaping. If that is right, then the collision left a thermal scar that is still affecting Uranus's behavior billions of years later. The tilt would be one consequence of the impact, and the cold exterior another. But here is where the clean story runs into trouble. Uranus has 5 large moons: Miranda, Ariel, Umbriel, Titania, and Oberon. All 5 orbit the planet's equator. Because Uranus is tilted 98 degrees, those orbits are essentially vertical relative to the solar system's plane. The moons go around Uranus's tilted equator like rings on a tilted hoop. If a single catastrophic impact suddenly knocked Uranus from a near upright position to its current sideways orientation, the existing moons should not have simply followed the equator to their new positions. Objects in orbit do not automatically realign when the planet beneath them is violently struck. A sudden knockout blow should have left the moons orbiting in their original plane, not neatly rearranged around the new equator. The moons, though, tell a different story, and that is the part that the single impact model has always struggled to explain cleanly. A newer theory proposes that Uranus was tipped over not by a visitor from outside, but by something it created itself. No rogue impactor from deep in the solar system. No catastrophic collision at a random angle. Instead, the culprit was a moon. A large moon that Uranus built in the ordinary way and then lost in the most destructive way imaginable. To understand why this theory exists, you need to know what moons typically do over time. They migrate. Earth's moon is drifting away from us right now, roughly 4 centimeters per year. This is not unusual. Tidal interactions between a planet and its moon transfer energy outward, slowly pushing the moon into a wider and wider orbit. It happens across the solar system. It is slow, it is steady, and under normal circumstances, it is completely harmless. But researchers studying Uranus asked a question that turns out to have a very unsettling answer. What if the moon migrates far enough that its gravitational pull starts interfering with the planet's own spin axis? What happens then? The math gets complicated fast, but the core idea is straightforward. As the moon moves outward, the gravitational coupling between the moon's orbit and the planet's rotation changes. At certain distances, that coupling becomes resonant, meaning the two motions start reinforcing each other in ways that are not stable. The planet's rotational axis begins to wobble. Then it begins to tilt, and as it tilts, the resonance strengthens, which pushes the tilt further still. It is a feedback loop written in gravity, and once it starts, nothing inside the system can stop it. Computer models show this process could drag Uranus from a relatively normal axial tilt all the way to around 80 degrees. At that point, the geometry of the system shifts into something genuinely chaotic. The moon's orbit and the planet's rotation are no longer in any kind of stable relationship. The moon's path begins to destabilize dramatically, and within a relatively short window in astronomical terms, the moon spirals inward and crashes back into Uranus. The planet absorbs it. The tilt, now pushed past 80 degrees by the chaos of that final phase, settles near its current value of 98 degrees, and the Moon simply ceases to exist. This is why the theory is so hard to immediately dismiss. It does not require anything exotic. Moons form, moons migrate. Resonances develop between spinning planets and orbiting moons throughout the solar system. Every piece of the mechanism is something physics already does in other places. The only unusual part is that the Moon in question was large enough and the migration fast enough to push Uranus past the point of no return. There is also something almost elegant about the way the theory handles the absence of evidence. One of the persistent, awkward questions about the giant impact model is why there is no surviving trace of whatever hit Uranus. A body large enough to tip a planet that size would have been enormous. Where did it go? With the migrating Moon model, the answer is built into the mechanism itself. The Moon that did this was always part of Uranus. It formed there, it migrated there, and it fell back in. There is no debris field to find, no unusual chemistry to explain. The system consumed the evidence of its own disruption. The theory is not without problems. The Moon required is substantial. Models suggest it would need to be at least half the mass of Earth's Moon to drive the tilt this far, and it would need to migrate at a rate fast enough for the resonance to build before the system found a different equilibrium. Whether those conditions were actually present in the early Uranian system is something researchers are still working out. But the model clears the basic hurdle. It is physically possible, it is consistent with known Moon behavior, and it produces a tilt close to what we observe. The Moon that tipped it would have erased all evidence of its own existence by falling back into the planet, leaving nothing behind except the permanent lean. Some researchers think Uranus was not knocked over once. They think it was knocked over twice, and that second hit, they argue, is the answer to the question that has been quietly undermining the single impact model for years. The problem was always the moons. Uranus has 5 large moons: Miranda, Ariel, Umbriel, Titania, and Oberon, and all of them orbit directly above the planet's equator. That sounds unremarkable until you remember what Uranus's equator actually is. It is tilted 98 degrees from vertical. The moons are circling a planet that is essentially lying on its side, and they are doing it in perfect alignment with that sideways tilt. If something enormous slammed into Uranus and flipped it in an instant, those moons should not have adjusted so cleanly. A sudden knockout blow would have left the existing moons on misaligned orbits, scattered and inclined relative to the new equatorial plane. Instead, they are orderly. They are neat. Something allowed them to settle into the equatorial configuration we see today, and a single sudden impact does not easily explain that. The two-impact hypothesis was developed precisely to resolve this. The key is timing. If both impacts happened early enough, before Uranus's large moons had fully assembled out of the disk of material surrounding the planet, the problem disappears. Here is how the sequence would have worked. The first impact tilts Uranus part way, not all the way to 98 degrees, but significantly. The planet is now off-axis, and the disk of gas and dust still orbiting it begins to slowly realign around the new equatorial plane. Then the second impact arrives, pushing Uranus the rest of the way to its current tilt. By the time it is over, the disk has had enough time and enough material to reorganize into an equatorial configuration around the planet's final orientation. The moons that eventually coalesce out of that disk form in the right plane because the disk itself is in the right plane. no contradiction, no scattered orbits. Simulations support this sequence. When researchers ran models of sequential impacts against a young Uranus, they found that 2 strikes of the right mass and geometry could reproduce both the planet's current tilt and the equatorial orbital arrangement of its moons. The timing constraint is tight. The impacts had to occur early, during the window when a substantial disk of material was still present around Uranus and had not yet finished assembling into moons. Miss that window, and the second impact creates the same problem as the first: fully formed moons on suddenly wrong orbits. What makes the 2-impact scenario more than just a patch for the moon problem is that it fits what scientists have increasingly come to expect about how the early solar system actually worked. The old picture was simple. Each planet had one dramatic origin story, one moon-forming impact for Earth, one spin-reversing impact for Venus, one knockout blow for Uranus. But the more closely researchers have studied the formation era, the messier the picture becomes. The giant impact phase of planet formation was not a single decisive moment. It was a prolonged period of repeated large collisions spread over tens of millions of years. Objects of enormous size were crossing each other's orbits constantly. 2 major impacts on a single planet was not an outlandish scenario. It was arguably expected. Earth's own history has grown more complicated under scrutiny. The moon-forming impact may itself have been more complex than a single clean collision. Mars shows signs of a dramatic ancient impact that reshaped its entire northern hemisphere. There is a growing sense among planetary scientists that the planets we see today are the products of overlapping catastrophes, not clean individual events, and that the simpler stories we told earlier were simplified because our models were not yet good enough to handle the messier truth. For Uranus, the 2-impact model does not close the case. The migrating moon theory offers a competing answer that requires no external impactor at all. Both models fit the data imperfectly and in different ways, but the double impact hypothesis carries the weight of a broader principle that is becoming harder to dismiss. The moons that circle Uranus's equator today may be the cleaned-up evidence of a history that was twice as violent as the simplest version of the story suggests. The axial tilt of Uranus did not just scramble its seasons. It reached deeper than that. It bent the planet's magnetic field into one of the strangest shapes in the solar system, a corkscrew of charged particles spinning through space at a tilt that makes no immediate sense when you first encounter the numbers. Here is what a normal planetary magnetic field looks like. Earth is a useful reference. Our magnetic poles sit close to our geographic poles, not perfectly aligned, but roughly in the same neighborhood. The North Magnetic Pole drifts slowly, but it stays in the Arctic. The axis of Earth's magnetic field is offset from the rotation axis by about 11 degrees. That is a small deviation. That is almost nothing. For most planets, the magnetic field and the rotation axis are close companions, tilted toward each other only slightly, generated by churning liquid metal deep in the interior, spinning in rough agreement with everything above it. Uranus threw that playbook away. Its magnetic field is tilted nearly 60 degrees from its rotation axis. 60 degrees. That is not a small deviation. That is not a drift. That is the magnetic field pointing in an almost completely different direction from the way the planet is spinning. And there is something else. Earth's magnetic field is centered roughly at the planet's core, which is where you would expect it to be generated. Uranus's magnetic field is not centered on the planet at all. It is offset from the center by about 1/3 of the planet's total radius, sitting somewhere in the interior like a magnet that someone placed slightly off to the side before sealing everything shut. Put those two facts together, the 60-degree tilt and the off-center origin, and the result is a magnetosphere unlike anything else in the solar system. As Uranus rotates, that lopsided, tilted field does not simply pulse or ripple. It tumbles, it wobbles, it sweeps through the surrounding space in a long, twisting corkscrew pattern, winding outward into the darkness behind the planet as Uranus rolls along its orbital path. Voyager 2 flew past Uranus in 1986 and sent back the first direct measurements of this field. Scientists at the time were genuinely startled. Nothing in the standard models of planetary interiors predicted a magnetic field this strange. Why does this matter beyond the strangeness itself? Because magnetic fields are not generated at random. They come from specific physical processes deep inside a planet, typically from electrically conducting fluid in motion, a dynamo working constantly in the interior. The fact that Uranus's dynamo is producing a field this tilted and this off-center tells you something is happening inside the planet that we do not yet fully understand. The interior of Uranus is almost certainly not structured the way the interior of Earth is. There is no sharp iron core. The leading picture is of a thick shell of pressurized water and ammonia and methane, conducting electricity under conditions so extreme that the fluid behaves more like a metal than a liquid. The dynamo that generates Uranus's magnetic field may live in this shell rather than at any central point, which would explain why the resulting field is offset from the center. And the axial tilt makes all of this dramatically worse for anyone trying to model it. On Earth, the rotation axis and the magnetic axis are close enough that the magnetosphere has an almost orderly shape. At Uranus, the two axes are pulling in nearly perpendicular directions, and neither one is pointing toward the Sun for any useful length of time, because Uranus is rolling on its side as it orbits. The magnetosphere flexes and twists continuously, never settling into a stable configuration, wrapping the planet in a dynamic, shifting envelope of charged particles that changes shape with every rotation. Every rotation of Uranus winds that field a little tighter, sweeping a corkscrew through space that has been turning for billions of years. Before going further, it is worth drawing a line between two different kinds of wrongness in the solar system. The wrongness of Venus and Uranus is a spin problem. Those planets rotate on their axes in directions that contradict the expected pattern inherited from the solar nebula. That is one kind of wrong. But there is a second kind, something that looks similar on the surface and is completely different underneath. Some objects in the solar system do not spin the wrong way. They orbit the wrong way. These are not the same phenomenon. They do not share the same causes, and mixing them up blurs the picture considerably. When a planet orbits the Sun, or a moon orbits a planet, the default direction is prograde, counterclockwise, viewed from above the solar system's north pole. The same original rotation that gave the planets their spin also set the direction of their orbits. Everything came from the same collapsing disk, and almost everything moves through space in the same direction because of it. The 8 planets all orbit the Sun prograde, without exception. The vast majority of moons orbit their planets prograde as well. This is not a coincidence. It is the direct inheritance of the solar nebula's angular momentum. The same rule that explains why Venus's retrograde spin stands out so sharply. But a handful of objects break that orbital rule. Small moons orbit certain planets in the wrong direction. Some asteroids trace retrograde paths. A few distant objects in the outer solar system loop backward relative to the general flow. These retrograde orbits are real, they are well documented, and they have nothing to do with how the objects themselves spin. A moon can orbit backward while rotating perfectly normally on its own axis. The two motions are independent. The mechanisms that flip an orbit are not the mechanisms that flip a spin, and understanding this separation matters. The most dramatic example of a retrograde orbit in the solar system is Triton. Neptune has 14 known moons. Most of them orbit in the expected prograde direction. Triton, the largest by a wide margin, does not. It circles Neptune backward, moving opposite to the planet's own rotation, on an orbit that is also significantly tilted relative to Neptune's equatorial plane. For a moon of its size, this is deeply unusual. Large moons that form alongside a planet almost always orbit prograde, because they assemble from the same disk of material that surrounded the planet during formation. A moon that arrives retrograde is a moon that did not form there. The explanation most scientists accept is that Triton was not born as a Neptunian moon at all. It was a Kuiper Belt object, a cold body from the outer reaches of the solar system that wandered too close to Neptune and got captured by the planet's gravity. The exact mechanism of that capture is still debated. One leading idea is that Triton originally traveled as part of a binary pair, two objects orbiting each other, and when they passed near Neptune, the gravitational interaction pulled Triton into orbit while ejecting its companion. Whatever the precise sequence, the outcome is a large moon traveling backward around a planet that had nothing to do with making it. Triton's retrograde orbit has consequences that are still unfolding. Because it orbits in the wrong direction, tidal forces between Triton and Neptune are gradually pulling Triton inward rather than pushing it outward, the way Earth's tides push the moon slowly away. In roughly 3.6 billion years, Triton will likely cross the Roche limit, the distance at which Neptune's tidal forces will tear it apart, and the debris may form a ring system around the planet. A captured moon, spiraling to its eventual destruction, all because it arrived from the wrong direction. None of this connects to the spin problem of Venus or Uranus. Triton's backward orbit is a story about gravitational capture and migration across the outer solar system. Venus's backward spin is a story about either a catastrophic ancient collision or billions of years of atmospheric and tidal forces reshaping a planet's rotation from the inside out. Uranus's tilted spin is a story about an axis knocked sideways and never recovered. 3 different planets, 3 different kinds of wrong, 3 separate chains of cause and effect with no shared origin. The mechanism that sent Triton into its backward orbit around Neptune had nothing to do with what happened to Venus or Uranus. Venus and Uranus are the most famous cases, but they are not alone. Pluto has an axial tilt of roughly 122 degrees. That puts it in the same category as Uranus by the standard astronomical convention, technically retrograde. Technically rolling through space at an angle that makes its poles do most of the work. And like Uranus, Pluto did not arrive at that tilt by accident. The leading explanation goes back to a collision, a large one, early in the solar system's history. Pluto's moon Charon is enormous relative to Pluto itself, so large that astronomers sometimes call them a double dwarf planet system rather than a planet and its satellite. The current thinking is that Charon formed the same way Earth's moon did, from the debris of a massive impact. That collision did not just create a moon, it redistributed the angular momentum of the entire system. The 122-degree tilt is the permanent record of that moment, still written into Pluto's rotation billions of years later. Other dwarf planets tell similarly complicated stories. Haumea, a compressed egg-shaped object out in the Kuiper belt, is one of the fastest rotating large bodies in the solar system. One full rotation takes less than 4 hours. At that speed, the centrifugal effect has physically stretched the planet into an elongated shape, wider at its equator than at its poles by a dramatic margin. Something had to spin it up that fast. The most likely candidate is a collision early in its history, one that transferred enough angular momentum to push its rotation rate to the edge of what the object's gravity can hold together. Eris, by contrast, rotates far more slowly. Different impacts, different outcomes, same chaotic origin story. What you start to see when you look across the full population of dwarf planets is that there is no standard spin state. Some rotate quickly, some slowly, some are tilted heavily, some nearly upright. There is no single number that describes what a dwarf planet's rotation looks like. This was because the collisions that produced these spin states were not operating from a single script. Each object got hit differently, at a different time, by a different mass traveling at a different angle. Comets and asteroids extend this picture even further. The spin states of small bodies in the solar system are genuinely chaotic in a way that the planets are not. Some asteroids rotate once every few hours. Others take weeks. A handful spins so fast they are classified as rubble piles on the edge of flying apart, held together only by gravity and friction. Rotating so quickly that if they spun even slightly faster, they would shed material from their surfaces. Some tumble in complex, non-principal axis rotation, meaning they are not spinning cleanly around a single axis, but wobbling through space in multiple directions at once, like a football thrown badly. This tumbling behavior typically means they were hit recently and have not had time to settle back into a clean rotation through internal energy dissipation. The Yorp effect adds another layer. Small asteroids can actually have their spin states altered gradually by the pressure of sunlight itself, photons hitting their surfaces unevenly and pushing them to spin faster or slower over millions of years. So even the rotation of a small rock in the asteroid belt is not purely the result of formation. It is the accumulation of every collision, every close gravitational encounter. Even the slow, constant push of light over the entire age of the solar system. What the small body population tells us, collectively, is that the collision-heavy picture of the early solar system is not a hypothesis built around two anomalous planets. It is confirmed in hundreds of thousands of objects, each one carrying a spin state that reflects its specific violent history. The planets are large enough that their spins eventually settle and stabilize. The smaller bodies retain more of the raw chaos, more of the individual fingerprints of specific impacts. The smaller the object, the more its spin looks like the record of every bad thing that ever happened to it. Neptune's largest moon should not exist the way it does. Triton orbits Neptune backward, not tilted, not offset by a few degrees, backward in the opposite direction from Neptune's own rotation and from nearly every other large moon in the solar system. If you watch Triton from above Neptune's north pole, you would see it moving clockwise while everything else moves counterclockwise. That single fact is a fingerprint. It points to something that happened a very long time ago and left a mark that has not faded in billions of years. The standard picture of moon formation is straightforward. When a planet coalesces from the early solar disk, material left over in orbit around it gradually clumps together. Those clumps inherit the rotation of the disk. They end up orbiting in the same direction as the planet spins, in roughly the same plane. This is how Earth got the moon. It is how Jupiter got its 4 large Galilean moons. It is how the system is supposed to work. Triton breaks every part of that picture. It orbits at a steep angle to Neptune's equator, and it does so in reverse. No moon that formed alongside Neptune from the same disk could end up doing that. The physics simply do not allow it, which means Triton did not form alongside Neptune. The leading explanation is that Triton came from somewhere else entirely, specifically from the Kuiper Belt, the vast reservoir of frozen objects beyond Neptune's orbit, the same region that contains Pluto. Triton's size, composition, and density all match what you would expect from a large Kuiper Belt object. It has nitrogen ice on its surface, methane frost, a thin atmosphere of nitrogen. Pluto has all of those things too. At some point, billions of years ago, Triton was probably a free-traveling body in the outer solar system. Then it wandered too close to Neptune. Gravity did the rest. Capture events are not simple. You cannot just fall into orbit around a planet. A free-moving object that passes a planet will swing around it and fly away again, like a stone flung from a sling. To get trapped, something has to bleed off enough energy to keep the object from escaping. One possibility is that Triton passed through a disk of material surrounding young Neptune and experienced enough drag to slow down. Another is that it arrived as part of a binary pair, 2 Kuiper Belt objects orbiting each other, and the gravitational interaction with Neptune split the pair, ejecting one object and capturing the other. This binary capture mechanism has gained traction in recent years. The math works, and it requires no special conditions beyond what the early solar system almost certainly had. What happened next was not quiet. Triton's arrival would have been catastrophic for whatever moons Neptune already had. A captured body coming in on a steep retrograde orbit would have crossed the orbits of the original moons repeatedly, pulling on them gravitationally, destabilizing them, flinging some outward and driving others into collisions. Astronomers think Neptune's current collection of small irregular moons, the ones tumbling on distant, tilted, chaotic orbits, are the debris. Fragments of moons that existed before Triton arrived and did not survive the encounter. The original moon system was largely erased. What is left is a graveyard of pieces, scattered on orbits that still carry the memory of the disruption. Triton itself is not permanent either. It orbits Neptune in a direction opposite to Neptune's rotation, which means tidal forces are working against it rather than with it. The same tidal mechanics that are slowly pushing Earth's moon outward are doing the opposite to Triton, pulling it inward. In roughly 3.6 billion years, Triton will cross the Roche limit, the boundary inside which a moon cannot hold itself together against tidal forces, and it will break apart. Neptune will briefly have a ring system that dwarfs anything in the solar system today, and then that too will disperse. What Triton survived crossing the outer solar system, and what it caused when it arrived, will eventually be erased by the same gravity that captured it. This is what makes Triton different from Venus and Uranus. The backward rotation of Venus is written into the planet itself. The tilt of Uranus is carried in its axis. But Triton's retrograde motion is orbital, not rotational. A record not of how a planet was hit, but of how a moon was stolen. Every time Triton completes another slow backward orbit around Neptune, it is quietly advertising the violence that placed it there. The solar system we live in today is a cleaned-up version of something much messier. The planets orbit in smooth, stable paths. The gaps between them are vast and mostly empty. Looking at it now, you could be forgiven for thinking that this was always the arrangement. It was not. What we see today is the survivor's version of a system that spent its first several 100 million years in a state of near constant violence. When the planets first finished assembling from the disk of gas and dust around the young sun, they were not alone. The solar system was crowded. There were hundreds of objects the size of small planets, protoplanets, planetary embryos, still drifting through the inner system on orbits that crossed each other's paths. Every crossing orbit was a loaded dice roll. Some of those encounters ended in a gravitational nudge. Others ended in collision. Impacts of genuinely enormous scale were not catastrophic exceptions. They were the expected outcome of the way planet formation works in its final stages. The giant impacts that researchers invoke to explain Venus's backward spin and Uranus's sideways tilt were not flukes. They were part of the standard process. Then, roughly 4 billion years ago, something shifted in the outer solar system. The giant planets, Jupiter, Saturn, Uranus, Neptune, were not always in the positions they occupy today. Gravitational interactions between them caused their orbits to shift. As they moved, their gravity scattered enormous quantities of debris. Billions of icy and rocky objects that had been sitting quietly in the outer reaches of the solar system suddenly found themselves on new trajectories, falling inward. This period is called the Late Heavy Bombardment. The evidence for it is written across the cratered surfaces of the Moon, Mercury, and Mars. For a period lasting possibly 100 to 200 million years, the inner solar system was being hit by a wave of material from the outside. The Moon's oldest craters date to this era, so do some of the scars on Mars that stretch for thousands of kilometers. In that environment, what happened to Venus and Uranus does not look exceptional. A planet-sized object hitting Venus and reversing its spin, or an impactor large enough to tip Uranus nearly on its side. These events sound extraordinary when you describe them in isolation. Set them against the backdrop of what the solar system was actually doing for the first billion years of its existence, and they start to look almost ordinary. The real question shifts. Not why did Venus and Uranus end up with such unusual rotations, but why did Earth, Mars, and Jupiter come through looking as normal as they do? Part of the answer is probably timing. The giant impacts that set Venus and Uranus on their current trajectories may have come relatively late in the formation process, after other planets had already settled into stable configurations. A planet that gets hit early has more time and more material available to modify the aftermath. A planet that gets hit after the surrounding disk has cleared has no such buffer. the impact leaves a mark that nothing can erase. Part of the answer may also be scale. Jupiter, the largest planet in the solar system by a significant margin, sits in a region where it would have experienced enormous gravitational interactions, but its sheer mass makes it resistant to being spun around by all but the most catastrophic collisions. Earth is smaller and more vulnerable, but it sits close enough to the Sun that it may have swept its orbital neighborhood more efficiently than Venus, clearing out potential impactors before they could do lasting damage. These are probabilities, not certainties. The early solar system was chaotic enough that luck was almost certainly a factor. What is striking, when you look at the full picture, is how much information about that violent period is preserved in the structures of the planets today. The axial tilts, the rotation rates, the presence or absence of large moons, all of these are fossils. They are records of impacts we cannot see and cannot replay. Venus spinning slowly backward, Uranus rolling on its side. These are not malfunctions. They are timestamps, physical memories of a period of extraordinary violence that the solar system has long since outgrown, but never fully erased. The miracle, in some sense, is not that Venus and Uranus were knocked around, but that so many other planets came through it all essentially intact. Because the impacts that shaped the planets happened billions of years before anyone was watching, computer simulations are essentially the only way to test whether a given explanation is physically possible. There is no recording, there is no fossil, there is no layer of rock you can dig up and hold in your hand that says a protoplanet hit Venus 4 billion years ago and flipped it backward. What scientists have instead are equations, processing power, and the ability to run a collision forward in time and see what comes out the other end. The basic approach works like this. Researchers take a virtual planet with known properties, mass, size, composition, rotation rate, and they throw something at it. They define the size of the impactor, its speed, the angle of approach, and then they let the physics run. The simulation tracks every parcel of material as it deforms, splashes, reaccretes, or escapes into space. At the end, they compare the result to what they actually observe. If the simulated outcome matches Venus's current rotation rate or Uranus's current tilt, the scenario is at least plausible. If it does not, it gets ruled out. What the simulations have shown, across decades of increasingly powerful computing, is that the range of impacts capable of producing Venus's retrograde spin is surprisingly wide. Head-on collisions work, oblique, glancing hits work, impactors the size of Mars work, impactors somewhat larger work. This is not a reassuring result in the way you might hope. It means the simulations confirm the general idea. A giant impact could absolutely flip Venus, but they cannot pinpoint which specific collision actually did it. The evidence allows dozens of different histories. For Uranus, the picture is similar. Simulations carried out by Jacob Kagereis and colleagues showed that a single impactor larger than Earth, striking at the right angle, can tip Uranus to its current 97.8-degree tilt. The numbers work, the physics checks out. But when researchers then looked at Uranus's moons, which orbit neatly around the planet's tilted equator, a single sudden impact created a problem. A sharp knockout blow would not automatically realign orbiting moons. They would keep moving in their original planes, at least for a while. The neat equatorial configuration of Uranus's large moons does not sit comfortably with a single violent flip. So researchers ran different scenarios, 2 impacts instead of 1, delivered early enough that the moons had not yet finished forming. The debris disk could then reorganize into an equatorial configuration as Uranus settled. Those simulations also worked, and that is precisely where the limits of the method start to show. When 2 completely different histories both produce outcomes that match what you observe, the simulation has not told you what happened. It has told you what is possible. That is genuinely useful. It rules out scenarios that fail completely, impactors too small to budge Uranus, collision angles that leave Venus spinning the right way. The impossible gets eliminated, but everything that survives the filter remains in play, and there can be many survivors. The problem runs deeper than just picking between 2 options. Every simulation depends on starting assumptions. What was Venus's original rotation rate before anything hit it? Nobody knows. What was the exact composition of the impactor? Unknown. Was the early solar system's debris field throwing large objects mostly from one direction, or equally from all directions? Contested. Adjust any of these inputs and the outputs shift. Different research teams, running what they describe as the same basic scenario, but with slightly different parameters, sometimes reach meaningfully different conclusions about which impact geometries succeed. This is not a failure of the science. It is an honest reflection of what the method can and cannot do. Simulations are the best tool available for this kind of deep-time forensics. They have transformed planetary science's ability to ask serious quantitative questions about events that left almost no direct evidence. The confirmation that a single large impactor can reproduce Uranus's tilt is not a small result. The demonstration that debris from a Venus impact tends to reaccrete rather than form a moon was a genuine insight that connected 2 separate observations. These are real discoveries. But the simulations operate under a hard ceiling. The early solar system was a specific place with a specific history that unfolded exactly once. The simulations explore the space of what could have happened, not the narrow path of what did. They are powerful enough to rule out impossible scenarios, and honest enough to show that several different histories can produce the same solar system. Step back from the individual cases and look at all the planetary spins together, and a pattern appears that raises its own questions. 6 of the 8 planets in the solar system rotate in the prograde direction, counterclockwise when viewed from above the Sun's north pole. The same direction they orbit, the same direction the original nebula was spinning 4.6 billion years ago. That is a strong signal. If the final stages of planet formation were truly random, if the giant impacts that shaped each planet arrived from completely unpredictable angles, the odds of any given planet ending up prograde rather than retrograde are roughly 50-50, like a coin flip. And yet, 6 out of 8 came up prograde. That is not the result you would expect from a purely random process. The numbers are not enormous enough to be conclusive on their own, but they are suggestive. Something during the formation of the solar system was biased toward prograde outcomes. The question is what? One possibility is that the impacts themselves were not random in direction. During the late stages of planet formation, most of the material in the solar system was still moving roughly in the same plane and in the same direction as everything else. The protoplanetary disk was not a 3-dimensional shooting gallery with objects flying in from every angle. It was more like a flat swarm, and most of the collisions happening inside it involved objects approaching each other on roughly coplanar, roughly prograde trajectories. A head-on collision between two bodies, both moving in the same orbital direction, is more likely to preserve a prograde spin than to create a retrograde one. The geometry of the disk itself may have been loading the dice. The other possibility is that prograde spin is more stable over time. A retrograde planet, rotating against the flow of the disk, might experience more disruptive gravitational torques from surrounding material, from nearby moons, from the sun's tidal pull. Over millions of years, some retrograde planets might have been nudged back toward prograde, leaving fewer of them in the final census. Whether this actually happens at the scale of terrestrial planets is not well established, but it is a real consideration. Then there is the other anomaly, the one that sits at the center of the whole accounting problem: the Sun. It contains more than 99% of all the mass in the solar system, which means it should, by any straightforward calculation, contain most of the angular momentum as well. It does not. The planets hold roughly 99% of the solar system's angular momentum, even though they contain less than 1% of its mass. Jupiter alone accounts for the majority of that. The Sun spins far more slowly than it should, given how much material collapsed into it. This imbalance is not a minor discrepancy. It is one of the biggest structural puzzles in the formation story. The explanation that most researchers accept involves magnetic braking. Early in the Sun's history, when it was still a young star embedded in the remnants of the collapsing nebula, its magnetic field coupled to the ionized gas around it. As the Sun tried to spin up, its magnetic field lines acted like a brake, transferring angular momentum outward into the surrounding disk, and eventually into the planets. The Sun slowed down. The disk and the planets sped up. This process is observed in other young stars today. It fits the physics. But the exact details of how much momentum was transferred, when it happened, and how efficiently it worked are still areas of active modeling. What makes this relevant to the individual spin histories of Venus and Uranus is that it shapes the baseline. The angular momentum that ended up in the planets came from somewhere. It was distributed across the disk before the planets fully formed, and whatever specific distribution it arrived in set the initial conditions for all the collisions that followed. The planets that ended up prograde, the planets that ended up retrograde, the planets that ended up sideways, all of them started from that inherited budget and were then modified by impacts, by tidal forces, by the specific chaotic accidents of what hit, what, and when. The solar system's spin history is a puzzle with most of its pieces in place, and just a few in the wrong spots, and working out how they got there is still an open problem. The wrong-way planets are not embarrassments in the solar system's story. They are something closer to the opposite. Every time a scientist points to Venus spinning backward, or Uranus rolling sideways on its orbit, that anomaly is doing real work. It is carrying evidence forward from a time when the solar system looked nothing like it does today. The question has never really been why these two planets are strange. The question is what their strangeness is telling us. Start with what their existence confirms. For decades, giant impacts were a theoretical construct, a convenient mechanism that planetary scientists invoked to explain things they could not otherwise account for. A collision here, a knocked-over planet there, but theoretical constructs need real evidence, and Venus and Uranus are exactly that. A planet does not rotate backward on its own. A planet does not tip to 97.8 degrees through ordinary evolution. Something enormous had to intervene, more than once, at more than one location in the solar system. That is not a minor footnote. That is confirmation that the final stages of planet formation were genuinely violent in ways that permanently altered outcomes. The impacts were real. The chaos was real. 2 planets are still carrying the marks. What this also tells us is that the solar system's current orderly appearance is misleading. Look at it today, and you see 8 planets moving in roughly the same plane, orbiting in the same direction, most of them spinning the same way. It feels like a stable, almost deliberate arrangement. It was not always this way. The neatness we see now is what survived billions of years of collisions, scattering, and gravitational reshuffling. Venus and Uranus are the places where the cleanup did not fully work, where the record of the original chaos is still visible in the motion of the planet itself. They are windows into a period that everything else has effectively erased. There is a deeper implication here too. The giant impact stage, that final phase of planet formation when large bodies were sweeping up the remaining debris and colliding with each other, was essentially random in its geometry. Impactors came from all directions. The angle, the speed, the mass of the incoming object, none of it was predetermined. Run the simulation again with slightly different starting conditions, and Venus might be prograde. Run it again, and Uranus might be upright. The outcomes were not locked in. They were drawn from a wide distribution of possibilities, and what we ended up with reflects one particular draw among many that were equally available. This has real consequences for how we think about other solar systems. If our own planets experience this degree of randomness during formation, there is no reason to think other planetary systems would be any different. Planets around other stars should show the same breadth of outcomes. Tilts ranging from nearly 0 all the way to fully inverted. Day lengths measured in hours or in centuries. Rotation axes pointing in all directions. The mild tilt distribution of our solar system, where most planets fall somewhere between 0 and 30 degrees of axial tilt, may actually be on the conservative end of what is possible. Venus and Uranus push that range outward, toward what a more typical result might look like when giant impacts are allowed to run their full course. There is also something specific in the comparison between these 2 planets worth holding on to. Venus and Uranus did not end up strange in the same way. Venus spins backward but nearly upright. Uranus spins sideways. Different geometries, different consequences, almost certainly different causes. The solar system did not produce one kind of wrongness. It produced at least 2, probably through different mechanisms operating at different times. That variety is itself information. It tells us that the processes capable of altering planetary spin are not rare edge cases. They are standard features of how planets are assembled. The 6 planets spinning in the expected direction are not the normal case with 2 exceptions attached. They are one possible outcome. Venus and Uranus are another. Both outcomes came from the same process, the same early solar system, the same physical rules. They are the most honest planets we have, the ones that kept the evidence of what planet formation actually looks like. Every time astronomers have looked at another solar system in detail, it has turned out to be stranger than expected. The first exoplanets discovered were enormous gas giants sitting absurdly close to their stars, orbiting in just a few Earth days. Nobody predicted that. The models built on our own solar system said planets that big should form far out in the cold, not practically skimming the stellar surface. But there they were, and that was only the beginning of the surprises. As the catalogue grew, something else started emerging from the data. A significant fraction of those close-in giants were not just orbiting fast, they were orbiting backward. Hot Jupiters on retrograde trajectories, circling their stars in the opposite direction from the star's own spin. In our solar system, every planet orbits the same way the Sun rotates. These systems had planets doing the opposite. Some were tilted nearly perpendicular to the stellar equator, tracing polar orbits that loop over the star's top and bottom rather than around its middle. The picture that had seemed obvious, that planets inherit their orbital direction from the same disk that formed the star, was falling apart system by system. Measuring any of this is genuinely difficult. You cannot look at a distant star and see a planet's axial tilt directly. Astronomers use a technique called the Rossiter-McLaughlin effect, which works by watching how a transiting planet distorts the light from a rotating star. As the star spins, one edge moves toward us and one moves away, shifting the light in measurable ways. When a planet crosses in front, it blocks different parts of that motion, depending on the angle of its orbit. The distortion tells you whether the planet is moving with the star's spin or against it. For tilt specifically, methods like asteroseismology, studying the oscillation frequencies of the star itself, can reveal how the star is oriented in space and allow comparisons with the orbital plane. Neither method is simple. Both require bright, well-studied systems. But together, they have now been applied to hundreds of planets, and the results are striking. Roughly a third of hot Jupiters examined this way show significant misalignment with their star's equator. Some are tilted more than 90 degrees. A handful are essentially retrograde. This is not a rounding error in the data. This is a pattern, and it is telling us something about how planetary systems actually evolve. The leading explanation involves a process called Kozai-Lidov cycling, where a distant companion, another star or a massive planet on a wide orbit, gravitationally tilts the inner planet's orbit over millions of years, pumping it into an increasingly extreme inclination until tidal friction from the star drags it inward and locks it into its final configuration. The result is a giant planet in a short, misaligned orbit, which is exactly what the observations show. What does any of this have to do with Venus and Uranus? Everything. The same forces that tilt a hot Jupiter can tilt the orbit of any planet, or its spin axis, or both. The forces are different in the details, but the underlying reality is the same. Planet formation is violent, chaotic, and does not reliably produce orderly results. Our solar system, with 8 planets mostly spinning the same direction, mostly tilted modestly, mostly orbiting in a common plane, is looking less and less like the standard outcome, and more like a relatively clean run through a process that usually produces more disorder. Some researchers have started asking whether solar systems like ours are in the minority across the galaxy. Systems with multiple large planets in stable, low inclination, prograde orbits may represent a lucky convergence of initial conditions rather than the expected default. The exoplanet catalogue is still incomplete, biased toward large planets close to their stars because those are easiest to detect. But even accounting for those biases, the sheer variety of orbital architectures being found suggests that the chaotic early conditions that gave us Venus's backward spin and Uranus's sideways tilt are not anomalies. They are standard features of how planets are assembled, playing out to greater or lesser extremes, depending on how each system's particular collisions and gravitational interactions fell. Our solar system, with its two misbehaving planets, may actually be one of the tidier examples the galaxy has on offer. For all the progress of the last few decades, the honest answer to the question of why Venus and Uranus spin the way they do is still incomplete. The broad strokes are there, the mechanisms are plausible, the simulations run, but the specific history of either planet, the actual sequence of events that produced what we see today, remains out of reach. Scientists have built compelling cases for multiple explanations, and the uncomfortable truth is that more than one of them fits the data. Take Venus. Two serious explanations are on the table. A giant impact early in the solar system's history could have reversed Venus's spin entirely. Alternatively, billions of years of gravitational tides from the Sun, combined with thermally driven atmospheric tides pushing back in the opposite direction, could have gradually nudged a prograde planet into retrograde rotation without any collision at all. Both of these explanations are mathematically consistent with Venus's current rotation rate. Both are physically plausible. Neither has been ruled out. And there is a third option that makes this harder, which is that both happened. A giant impact might have set the initial conditions, and tidal forces then spent billions of years fine-tuning the result. When two independent mechanisms can each explain the same outcome on their own, and can also work together, it becomes nearly impossible to identify which one did the actual work. The deeper problem is Venus's interior. The atmospheric tidal torque model depends on how energy dissipates inside the planet, and scientists do not have good enough constraints on Venus's internal structure to pin that number down. Without it, the model has a free parameter that can be adjusted to match the observations, almost regardless of what the observations are. That is not a flaw in the science, it is just an honest account of what happens when you are trying to reconstruct a planet's billion-year history from measurements taken at its surface and from orbit. What you need is a seismometer on Venus, or a long-duration lander capable of measuring the planet's internal properties directly. Those missions have been proposed. None have flown. Uranus is not in a cleaner position. 3 separate hypotheses have serious support. A single giant impact from a large protoplanet is the oldest and most cited explanation. 2 sequential impacts, timed early enough that the current moons could still form from a reorganized debris disk, solves the moon problem that the single impact theory struggles with. And the migrating moon hypothesis, in which a large internal moon gradually destabilized Uranus's axis before falling back into the planet, requires no external impactor at all. Each of these scenarios has been modeled. Each produces outcomes consistent with what we observe. And because all 3 options converge on roughly the same end state, the current configuration of Uranus cannot tell us which path it arrived by. This is the wall that simulation-based planetary science runs into regularly. The models are powerful enough to show that a given scenario is possible, but not always powerful enough to show that it was unique. Different research teams with different assumptions and different initial parameters run their simulations and sometimes reach different conclusions. The literature on Uranus's tilt contains papers supporting each of the major hypotheses, often from equally rigorous groups using equally sophisticated tools. That is not a sign that the field is confused. It is a sign that the problem is genuinely hard. What would change things? Better data from Venus's interior would constrain the tidal model significantly. A confirmed detection of an ancient impact basin on Uranus, if such a structure survived in some form, would strengthen the impact case. Observations of exoplanets caught mid-formation might reveal how common these tilting events actually are. Each piece narrows the space of plausible histories, even if none of them closes the case alone. The frontier here is not a failure of imagination. Every major mechanism on the table is a serious physical hypothesis backed by real mathematics. The problem is that the events happened 4 billion years ago, left only indirect traces, and can only be approached through inference. The answer is out there somewhere in the physics, preserved in the structures of the planets themselves, waiting for better instruments and better models to read it. There is something worth sitting with in all of this. Every time a telescope locks onto Venus or Uranus and measures the direction of its spin, it is not reading a current condition. It is reading a record. The way a planet rotates is one of the oldest pieces of information about it that physics has preserved, unchanged for billions of years, still sitting there, encoded in the motion of a world, waiting for someone with the right instruments to ask the right question. Think about what planetary spin actually is. It is angular momentum left over from the first chaotic moments of solar system assembly. Most of it never goes anywhere. It just keeps turning, the same direction, the same rough rate, carrying forward whatever was true about that planet in the first few 100 million years of its existence. The geological surface changes, the atmosphere evolves, oceans appear and disappear, but the spin, by and large, persists. When Venus completed its first backward rotation somewhere around 4 billion years ago, whatever caused that rotation had already happened. A collision, a slow atmospheric push, some combination of forces we still cannot fully untangle. The cause was over. The spin remained. This is what makes the question so strange and so difficult at the same time. When astronomers ask why Venus rotates backward, they are not really asking about Venus as it exists today. They are asking about an event or a process that concluded before the Earth had finished forming, before any continent existed, before the oceans filled, before the first cell divided in some warm, shallow pool somewhere on this planet. Whatever made Venus spin the wrong way happened before any of that. And we are standing here now, billions of years later, trying to reconstruct it from the motion that it left behind. It is not so different from the light coming from a distant star. When you look at Betelgeuse in the night sky, the light entering your eye left that star around 650 years ago. The star you are seeing is not the star that exists now. It is a message. It left before the printing press existed. It has been crossing space ever since, carrying information about a moment that is permanently out of reach. Planetary spin works the same way. Venus's retrograde rotation is a message that left the early solar system roughly 4 billion years ago and has been arriving continuously, every single day since then. We only recently learned how to read it, and we are still arguing about what it says. The fact that we cannot settle the question cleanly is not a failure. It is an honest reflection of how far back the question reaches. The impact that may have flipped Venus happened before Earth's moon existed. The process that may have slowly nudged Venus into its current retrograde equilibrium operated over timescales that dwarf all of recorded human history by a factor that is almost meaningless to write down. We are asking the rocks and the orbits and the spin directions to testify about something they witnessed before they were fully formed. What we can extract from them through radar measurements and atmospheric models and computer simulations is genuinely remarkable. That we cannot extract a clean single answer is simply the shape of the problem, and somewhere in that gap between what we can measure and what we can know for certain is where the real picture of planetary formation lives. Not the clean textbook version, the actual one, full of massive collisions nobody witnessed, gradual forces operating on timescales too long for any civilization to observe directly, outcomes that look orderly from the outside and chaotic from the inside. Venus and Uranus are not footnotes to the story of the solar system. They are the places where that story left the most legible marks. Right now, without anyone watching and without any drama, Venus is turning slowly backward in the dark, the same way it has been turning since before life existed on Earth.